This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll go over the basics of covalent compounds and then talk about how to name them, and then we'll go over the most important intermolecular forces. Covalent bonds are usually formed between two nonmetals, and the bond in a covalent bond is formed by the sharing of electrons. So the two atoms that are connected by a covalent bond, there are electrons that are orbiting both of those atoms. And it's not every electron that those atoms have, but it's some of the valence electrons that are orbiting. And covalent bonds, a single covalent bond means that there are two electrons orbiting those two atoms. And then if you have a double bond, that would be 4 electrons. If you have a triple bond, that would be 6 electrons. And it is those shared electrons that holds the atoms together. So contrary to ionic bonds, where ionic bonds are held together because of the attraction between two opposite charges, in covalent bonds, neither of the atoms has any charge. And the naming that we use for covalent bonds is a little bit different. If you remember from ionic compounds, when we named them, we didn't have to use any prefixes like what we have in this table here, because when we had the name of an ionic bond, we could tell how many of each atom there was because of the charges, because the charges had to cancel each other out. So that allowed us to calculate how many of each atom there would be. But for covalent bonds, there's no charges to cancel out, so we have to use these prefixes in order to know how many of each atom there are. And the prefixes are really easy to apply because they're all words that you're probably already familiar with. The only rule that we need to apply is that whenever the first element, so here we have phosphorus, whenever the first element, there's only one of that element, so there's only one phosphorus here, you don't use a prefix. You just write it as normal. So for this one, we would just write phosphorus without any change. And then you would do the prefix for the second one. You'll always do a prefix for the second one, and then that would be tri. And then you would think it'd be chlorine, but we changed the ending to IDE, just like what we did for ionic compounds. So the ending is IDE. Yeah, and all these rules, these are for binary covalent compounds. So only compounds that have only 2 elements in them. And the next one, so let's do the next example. Now we have 2 of the first one, so this time we actually will use the prefix. So this one would be dinitrogen. The first word is unchanged, besides maybe a prefix. And then the next one is oxygen, so that will be oxide. But there are 3 of it, so we'll do trioxide. So dinitrogen trioxide. And then the next one, there's only 1 carbon. So think of what prefix you get. If there's only 1 of the first element, it does not get a prefix. So that is carbon. And then there's only 1 of the oxygen, but it's the second one. So we do put mono. Whenever the second element, there's only 1 of it, we do put mono. So carbon monoxide. Before we talk about intermolecular forces, we need to talk about polarity. And polarity uses the concept of electronegativity. So if you remember from the video about periodic table trends, we talked about electronegativity. And if you have 2 elements bonded to each other, and one of the atoms is way more electronegative than the other, then it's going to pull the electrons in that covalent bond towards it. So for example, if we have a carbon bonded to an oxygen, the oxygen is more electronegative. So it's going to pull the electrons in that bond towards itself. But this does not mean that the electrons will only be on oxygen. So the electrons are still going to be orbiting around carbon and around oxygen, but they will just tend to be closer to oxygen, and then they'll just spend more time around oxygen. So since the electrons tend to be closer to oxygen, the oxygen gets a partial negative charge, which we represent with this symbol here. So that's partial negative. And then the carbon is missing some electron density, so then that gets a partial positive. And again, it's just super important to emphasize that these electrons are still orbiting around carbon and oxygen. They just tend to be closer to oxygen. So that's why it's only a partial charge. So this is not an ionic charge where those are complete full positive or full negative charges. These are just partial charges. And by far the most common polar molecules you'll see on the MCAT are OH bonds, NH bonds, and then CO bonds. And then the CO bonds, sometimes they will be COO bonds. So just be aware that you need to recognize all 3 of those as polar bonds. The first intermolecular interaction that we're going to look at is dipole interactions. So a dipole is just another name for a polar bond. So here we have a C double bonded to an O, which is polar, so this is also a dipole. And if we had a solution of this molecule, so we have millions of this exact molecule, they're going to line up in a way that the partial negative charges are lined up with the partial positive charges of other molecules. So if we just draw underneath of this another one of this molecule, we can see that how it lines up, the partial negative of that oxygen is going to line up with that partial positive of the carbon above it. And then we represent the attraction between them with just a dotted line. So that dotted line shows that they are attracted to each other and there is some force holding them together. So then this whole thing, this attraction between them, that is your dipole interaction. And this doesn't happen with just COs. This happens with any polar bonds where you see the partial negative and partial positive charges lining up. And these types of interactions will become really important when you think about boiling point and some different types of chromatography, which we'll cover all of that later in videos that are more about those specific things. But what you can think about now is that the stronger and the more intermolecular forces you have, so dipole interactions are a type of those, the more of these you have, the higher the boiling point will be, because these molecules are better at sticking together. Where when you have molecules that don't do well at sticking together because they're not attracted to each other, substances like that will have really low boiling points because the molecules will be really easy to get to spread apart and not stay together. Next, we have hydrogen bonding, which is a type of dipole interaction. So this should be using all the same principles as before, where we have a polar bond, and the polar bond creates a partial positive and a partial negative charge. And then when you have a substance that has tons of these molecules, they align themselves in a way that the partial negative and partial positive charges line up and have that attraction between each other. And the two really big ones that you want to be aware of are OH and NH. So those will be the two ones that you see the most on the MCAT. Sometimes they talk about FH being a popular hydrogen bond molecule, but that one really I haven't seen that come up on the test a whole lot. So the first two I would definitely make sure that you're really, really aware of. And something that they always emphasize is water. So water has an O bonded to two H's. So it's actually got extensive hydrogen bonding because we have one partial negative and then two partial positive charges. And then just to illustrate how this lines up, so if we had another water molecule underneath of that first water molecule, we just draw out all of our partial charges and then draw that dotted line to show the interaction between them. So you can imagine whenever you have millions of these, how extensive that aligning of these partial charges could be, which gives water and other things with hydrogen bonds a really high boiling points and really strong intermolecular interactions. And it's worth pointing out that H bonds are going to be stronger than other types of dipole interactions. So yes, they are a type of dipole interaction, but they are the strongest type of dipole interaction. The last one we'll look at are London dispersion forces. So London dispersion forces are special because they happen to non-polar molecules. And before we look at these, we want to establish the idea that electrons are moving around molecules. So electrons are not stationary, which you're probably already familiar with, but it's really important in order to understand these. So if we look at our methane on the left, which is a nonpolar molecule because it's C attached to H, and those electronegativities aren't different enough for that to be a polar bond. So those are nonpolar bonds. And we're going to pretend that just by pure chance, a chunk of the electrons in this molecule happen to kind of aggregate on the right side of that methane. So that, again, that's just by pure chance, those electrons just happen to all be over on that side. So that's going to give us a really weak and a very temporary partial negative charge on that part of that methane molecule. And then what that's going to do to the methane on the right is it's going to push those electrons that are on the left side. It's going to push those electrons over to the right. So then the right side of our methane on the right will be where those electrons aggregate, because the electrons from the methane on the left push them away, because remember, like charges repel each other. So then that's going to create a partial positive on our neighboring methane, and then also that partial negative on the other side of the methane. And we'll also have a partial positive on that initial methane too, which the one on the left happened by pure chance, and then the one on the right was induced by the one on the left. And these interactions are really weak and they're really temporary. So after just a tiny bit of time passes, the electrons will redistribute and they'll be evenly distributed, and then you're not going to have these partial charges anymore. But it's still really significant because it leads us to be able to identify what nonpolar molecules are going to have stronger London dispersion forces. And what you want to think about is the amount of contact area that nonpolar molecules can have with each other. So for example, let's just draw a chain of hydrocarbons down here. And so if we had a solution of a bunch of this molecule, which is just this chain of hydrocarbons, they can do what we would just call stacking. And they can kind of fit together like a puzzle piece. And so you can imagine, since they have so much contact area, there's just a lot of opportunity for these London dispersion forces to happen. Where if we have something that maybe is branched, so we have something that's branched like that, if we have a bunch of those molecules, they can't stack together as well as the molecule on the left can stack together. So then the one on the left has stronger London dispersion forces. So then, like we talked about just earlier in the video, it's going to have things like a higher boiling point and just some different characteristics because of those stronger intermolecular interactions. So just keep that in mind whenever you're looking at polar molecules and it's a question that's involving intermolecular forces. You really want to be thinking mostly about stacking and how much can these molecules have contact area between each other. And there's a couple more factors that play into boiling point, but those will be discussed in later videos.